Good morning, everybody. Thanks for being here. The first talk after the conference dinner, it's always hard, so thanks a lot. I hope it won't be too hard. So I'm here just to talk about the ALFOSC data successful loan, and in fact, I'm going to focus on successful because I think it has been. I will try to show you that that is true, and in fact, it will be consciously biased, what I'm going to talk about, because I'm going to be focused on this relationship, the IAA, so the institute where I'm working on, and the ALFOSC. And just to, that I'm sure that you know what it is, that it is coming from the Instituto de Astrofisica Andalucia, because most of you, I'm sure you have used ALFOSC, so you are supposed to have used this sentence, in which is said. And so my talk also will be taking into account that results that at least in part have been done by this ensemble, the IAA and ALFOSC. Good. So the outline will be more or less a chronological history of what we have been doing with ALFOSC since the beginning, and I've divided that in such a way as being more or less until the age of majority, so the first 18 years, and then mainly focused on the last 5 years, and talking mainly about minor bodies, blazars, nova shells, planetary nebulae, and a little bit on outflows in liners, but it'll be a subject of a dedicated talk after the coffee. So these agreements started almost 25 years ago, so we have to celebrate this year I don't know the name in English, should be the silver wedding or something. And the agreement provided with the partners, so the University of Copenhagen and the IAA, with 14 nights per year, and it has been so for these 25 years. I mean, it changed then for 12, but anyway. And just at the very beginning, so Hugo Schwartz already reported that about 80 or 90% of the not requested time at the very beginning was already for ALFOSC, and that it was the instrument with the smallest downtime being used at the observatory of Roque de los Muchachos. And then the first IAA projects with ALFOSC were focused on planetary nebulae, proper motions in heavy haro objects, and dwarf galaxies in Higgs and Kuiper groups. In the following years, I don't see from here, but so in the 2000, 2003 or so, the second renovation of the agreement, it was the same thing. Less than 10% was lost to technical problems, and 30% for bad weathers. And the subjects of research I will talk about later in some more detail. So I was thinking about. I mean, I wrote down here what means ALFOSC, but Amanda already said so. It was a surprise. So it comes from Alhambra, of course, in Granada. And I'd like to point out here that the coordinators of the guarantee time for ALFOSC at the IAA have been these people here. First, Josefa Masegosa, then Antonio Delgado, that I think it is here, or it was here some minutes ago, Javier Gorosabel, Martin Guerrero, and myself in the last years. So in the first years, as I said, the research was focused mainly on the obtaining data for deriving the spectral energy distributions of the host galaxies, or GRBs, with these people mainly involved in the IAA, Castro Tirado and Gorosabel, but I'm not going to put any detail on here. I'd like to, I will be focusing a little bit on this project, which was the analysis of the star formation in nearby cluster galaxies, in some of the best known clusters of galaxies, and here you have an image of one of those, so Abel 1363, and that it's for an image is an H alpha image is a bit not so pretty. So just to put in context, here is the image of the whole cluster. Galaxies in the clusters are placed in this direction. So the two objects that you could see in the image before, so these two galaxies, are these two here. So With an enlarged view, you see here these two irregular galaxies, and the H-alpha imaging made available not only distribution of H2 regions in these two irregular galaxies with arcs that were pointing towards the center of the cluster in this direction, but also the deep H-alpha image provided for the first time this extension. These two galaxies are these two here, there. So the quantification of the extension size and luminosity of these tails that were amounted to almost 75 kiloparsecs, and that were analyzed in the context of being produced, because of their properties due to ram pressure stripping. Another important contribution was to determine the star formation history, so the star populations of low luminosity AGNs, with the work that also used imaging spectroscopy mainly, and also HST image together, and that resulted in Seafood galaxies having not a strong contribution of massive hot stars, and having an important intermediate H-star distributions in at least 1/3 of them, and they were published in papers that have still are being cited today. Then we ourselves contributed to a study of the properties of the most luminous galaxies among ultraluminous infrared galaxies with broadband imaging with NOT, in which we showed firstly that the images were very much comparable to those coming from the HST with respect to the details we could obtain. This is the same object here and there, so this is with HST. But also we could reach much deeper, of course, because we pose longer, and to get the details of the tidal tails in these galaxies, which resulted to be, in most cases, coming from mergers. So it was quite an unexpected result, because at the epoch, these numerical simulations showed that the resulting galaxies from mergers should be more close to ellipticals. And we found that almost 25% had disks, and then it has been shown that the disk can resist such mergers, and simulations reproduce that disk can also be there. Then I won't give any detail on this on Planetary Nebula, because I will show more recent results later on, but I'd like to stress the results on the study of a thorough study of Higgs and compact groups, galaxies in Higgs and compact groups, considering also the H1 content, and the deficiency and morphology of the distribution of the atomic gas in such high-density objects. But also I'd like to stress the thesis by María Ángeles Martínez Carballo, who was based mainly on spectroscopy obtained with ALFOSC, and also with CAFOS in Caja, and the telescope, the spectrograph in San Pedro Mártir, analyzing the deficiency of broad-lined AGNs in these very, very high-density environments. And in fact, this is another. All what I'm showing are images. The pictures are always coming from ALFOSC. This is another example of a Higgs compact group, and this is probably you don't see the farthest distance from the screen. This is a typical spectrum. This is the one coming from this galaxy there, so Higgs G. And with this spectroscopy, they could obtain not only the percentage of emission line galaxies, and among them how many of them were AGN, either of type 2 or type 1, but also to analyze the stellar populations by making analysis of the stellar synthesis, stellar population synthesis, and analyzing the ages of the stellar populations in these galaxies as compared to, these are about 200 galaxies in compact groups, which compares to about 300 galaxies in isolated galaxies coming from the sample from the catalog by Karachentsev. And the results showed that the galaxies in Higgs and compact groups were older, with shorter star formations, and this was independent of the morphology or mass or luminosity, because they were compared in different pairs. Ending the age of the majority, I'd like to show you here. This comes, the left-hand side comes from the plot from the NOT webpage. So here you see the combination of publications coming from the different instruments in 2013, 14, and 15. Together with ALFOSC, you see this, I mean, you probably don't see the number, this 43, almost 43%, but you can see the, I mean, roughly the percentage. And here, this is my own elaboration with the publication list that they provide also the web page of the knot, where I've considered those publications having used ALFOSC. So here, this is from this line, from the dotted line leftwards. This comes from the numbers provided by the web page, and this is my own elaboration. So it probably not free from errors. So I mean, but roughly it should be more or less okay. In total, there are 460 papers from KNOT since 2015, and this is a percentage of papers with ALFOSC contribution, which moves from 40-something to almost 80% in this year, which is partial, of course, because it has not ended yet. And I've made my own distribution in subjects of these papers, and just to show you here that for supernovae or novae, almost 35% of the publications are made, and also from smaller contributions for other kind of transients, as radio burst or tidal disruption events, or also GRBs. And there's also contribution for follow-up of big projects like MAGIC, ZDF, Gaia, Planck, and also planetary nebula there, asteroid, comets, and even exoplanets in the same category. But I'd like also to stress that for extragalactic astronomy, which is my field of research, so that's one of the biases I have, there are also a number of studies published on galaxies and cluster of galaxies, and also quasars and AGNs there. And just to show an example of a paper in Nature with this kind of follow-up results in big collaborations coming from the study of the Compton emission in a long gamma ray burst, where both imaging and spectroscopy from ALFOSC were very, very useful, and in fact absolutely needed for determining the redshift of the object. Good. So in the last 5 years, I will give you again a biased view, because this is coming from IAA. While I'm talking, I'll show you a video which is not true. It's just artistic picture and of a minor body, Aomea, in the solar system. And I don't know if it will come with music, but anyway, it makes more chic. So yes, so this is always a way to show you that we have changed our logo, because it was before we changed it. So the new one is here and the old one is there. So anyway, so this is of course not true, and but from data from different telescopes and places on Earth, and by the process of stellar occultation, they could determine to have an idea of what it looks like. So size, access ratio, and even the presence of a ring around it, which is one of the first rings detected in such kind of objects. But ALFOSC was absolutely important. The observations made 1 month before the stellar occultation to make a very precise prediction of how the occultation will be. And thanks to that, they could determine all these properties. And very recently, so last year, we also had, they had results from a comet called 8P that was discovered by Méchain in the in 1790, and then rediscovered by Tuttle, and who was the one who established the period. And with data from 2008, there was, in 2021 it was a repass of, but the data, it was too close to the sun, so the data couldn't be used. And with ALFOSC, our imaging and spectra, they could determine both these two things. What I'm showing here is the comparison of the dust model predictions in red with the observations, with the isophotes in black, so it's almost a one-to-one relation. And from the spectra, they derived the gas production rates, in fact, to show that it is a comet that could be used as a backup object, so the Comet Interceptor mission, in which we are very, very strongly involved at the IAA. And because you probably know, this instrument, this satellite or whatever, this mission will be waiting for having the right comet, but in case it doesn't appear, they need to have a list of backup objects, and this one seems to be one of the most, one of the best candidates for that. And that's all, because it doesn't work. Yes, it doesn't work. That way. So, and if I do, yes, fine. So another result I'd like to stress is this one, with the study of a blazar, and they were both imaging for the spectral energy distribution and the spectra for trying to understand how the spectral properties were changing with the time. In red, you see the ALFOSC spectra considered in this work in a Nature publication. There were both, and multi-wavelength data, of course, were used to determine what was the origin of the variability observed, and that they concluded that it can be explained based on an homogeneous curved jet with changing orientation that confirmed the relativistic beaming theory. And coming to nova, I wrote down here, since I'm not an expert what a nova is, but we were explained already yesterday, so I won't give any detail here. You all know. And while I'm speaking, I will show you a video of one of these objects. So this one, DQ Hercule, in which you see how the different images taken from ALFOSC starting in 1997, provided us with the change of the expansion, of the shell expansion with the time. And in fact, for these objects, they could measure the angular expansion rates, which were compatible with having free expansion, and the prediction of being constant in the next few hundred years or so. And another, this is a result from 2 years ago, and another more recent one from this year already is this one, when they study other nova remnants, two of them in common, where they used intermediate and narrowband imaging from ALFOSC and also high dispersion spectra from other places, and they use that with the 3D shaped software, in which they can. This is the same object as you have here. That's one, DQ Hercule, and here this is the image with the long. You probably won't see that, but there's a long slit trace in north-south here, and then another one in the diagonal. This one, and you have the observed position velocity diagrams, and at the bottom you have what they obtained from the modeling, in which, I mean, they show that they can quite nicely reproduce the morphology and the kinematics in these objects. In planetary nebulae, one of the results that were quite nice and new were the derivation of the history of this nebula on the Hubble. I don't know if it is pronounced like that, Hubble 1 or Hubble 1, I don't know, and where they showed that the ionization structure was opposite to what one should expect, because the ionization was much higher towards the center, and they interpreted this as coming from a born-again star, which was produced the second structure in the shell. And both imaging at narrowband, with narrowband filters and spectroscopy from ALFOSC were used. I haven't said, but someone already said it yesterday. It's great that we have such a wonderful set of narrowband filters in NOT. It was you, yes. And in fact, it's very useful for a kind of projects like this one. That's another ones that I talked about. It's unrivaled, I think. It's really very nice. Another thing concerning planetary nebulae, in which staff from Institute was contributed, was the first deep image catalog of extended IFAS planetary nebulae, where they make an atlas of 58 deep images, and they can classify in true, likely, and possible extended planetary nebulae based on narrowband imaging in oxygen 3, H alpha, and nitrogen 2. So these are the columns for different objects, and this is a composite color-coded image to know how the structure of this object is. And much more recently, so this year, this is a study of the planetary nebula 6905 and its central star, where with both, again, narrowband imaging and spectroscopy, you see here the wealth of information on the chemical composition and the physical properties of this central star are, and they obtained an unprecedented detail on the ionization structure of this nebula and also on the central star. And so with using models, they could provide even the mass of the progenitor and things like that. So quite nice and quite detailed study. This is almost my last transparency. Good. So I will be on time, I guess. So just to end with this is my field of research. I have just one transparency. So this is because you will have a talk after the coffee, which will describe all this work in detail. But just to show, these are beautiful images. I had a colleague in the IAPA that was a theoretician whose opinion was that galaxies were always the same. When I look at that pretty image that they always say that galaxies are always the same. I don't agree. So I think this is a beautiful image of a galaxy taken from, this is NGC 4321, right? And this is a color-coded in which you see the H-alpha emission and over the continuum of this galaxy, both at larger scales and in the central regions. And this information, together with spectroscopy, is used to determine the possibility of having outflows in these kind of objects, which are LINES, low ionization, narrow emission regions, or kind of AGN, which are very, very low power. So you will have all the details after the coffee break of these analysis, which is the most numerous atlas of objects of this kind, which is almost, 70 objects. And just to end with, I'm really proud of being here. I thank the organizers for having invited me. Not only because I'm glad to be here because I have been using ALFOSC, but also because I have been connected to ALFOSC since the very beginning. Since when I was a baby on research. I started my PhD in January, last century, of course, 1991. In January, and in May, I went to my first meeting in Sweden, in Gothenburg, and in passing, we stopped in the observatory of Copenhagen because there was already the work together with the observatory in the construction of ALFOSC. I had no idea of what it was, of course, because I had been just 5-month baby, and but I was there with Johan. We had dinner in his house as well, and I remember that as one of the things that I could never forget, of course. And I'd like to say here that then I met, a cross-by with Johannes when I was at the IAP. He was the general secretary of the IAU. So it's the kind of connection that you have in life. You don't know why, and here I am in this meeting in honor of himself. And I love what the organizers have put on the bottom of the webpage: science, instrumentation, and education. I couldn't imagine another person in which these three so important things for research are put together, because we cannot do science without instrumentation and without education. So it's an honor, as I was saying, for me to be here just to honor Johannes, and that's all. Thank you.